Well, hi everybody. Welcome to the first review video for the second unit. We got a lot to talk about today. We're going to talk a little bit about twin concordance and what we can do with those numbers. We'll give you some examples of reading pedigrees. That'll come in handy in the future. And then we'll talk a little bit about gene linkage and define coupled and repulsion and give you just a way to look at those questions in a little bit more of a straightforward way. First off, though, I want to apologize for the shadow here. We do have Jet just to the left of the board. In fact, this is Jet's blanket. So if you see movement of the shadow, that's just him resettling here. He wants to take a nap next to Dad today. So first thing about concordance. A lot of you were expressing that you're not even quite comfortable with what concordance is. Well, concordance is the percent of twins. And this can be identical monozygotic twins or fraternal twins, which are dizygotic. Let me just try to get that focused better. The percent of twins, and probably the easiest way to say it, is it's the percent of twins that match for a trait. So if we have 30% concordance for a trait, and the example that I used for some of you in the feedback that I gave in Edpuzzle was for handedness. So let's say we've got 30% concordance for handedness. We just mean, are you right-handed or left-handed? What we can do is imagine that we're in a room and there are 10 sets or pairs of twins. And let's imagine for 2 of those sets of twins, both twins, so for 2 sets, both twins are right-handed. And let's say for another set of twins, a single set of twins, both twins are left-handed. And for the remaining 7 sets of twins, each twin uses a different hand. So one is right-handed and one is left-handed. If that's the case, then we've got 30%, or 3 of the total 10 sets of twins, 30% of the twins match for the trait. 2 of them match because they're both right-handed, 1 of them matches because they're both left-handed, but 3 out of the 10, or 30% of the twins, match for the trait, and the remaining 7 sets of twins, or 70%, don't match. So that's all we mean for concordance. So if we're talking about a widow's peak, 50% concordance means that 50% of the twins being studied either both have the widow's peak or both don't. The most important thing is that 50% of them match, and the other 50% didn't match, meaning one twin had a widow's peak and one twin didn't. So that's what we mean by concordance. Now, with that in mind, what we want to think about is how are these twins different? So monozygotic twins, also known as identical twins, they come from a single zygote, they share quite a few things, don't they? They share their genetics, because monozygotic twins are 100% genetically identical. They're clones of each other. And they share their environment, meaning they're born to the same parents at the same time, they're eating the same food, they're exposed to the same environmental pollutants, they're in the same home environment, they go to the same school, etc. So monozygotic twins have the same exact genetics and nearly the same exact environment. Dizygotic twins, well, those are fraternal twins. They're born at the same time. They're in the womb at the same time. They go to the same school. They eat the same food. They're around their parents at the same time. They're in the same home environment. Dizygotic twins have nearly an identical environment. But because they're nothing more than siblings, they don't have identical genetics. So if we take the concordance of monozygotic twins, which represents genetic and environmental similarities, and we subtract from it the dizygotic concordance, which is largely due to environmental similarities only, what are we left with? Well, let's look at it. If we take the genetics and the environment and we subtract out the environment, we're left with the genetic component of the trait. And so that's what we use this differential of concordance for. We use it for determining the genetic component of the trait. So if I've got a trait where in monozygotic twins the concordance is 75%, and then dizygotic twins, the concordance for that trait is 15%. And let's not lose sight of what we mean. What we mean is that when twins are identical, 75% of the twins for that trait, if they're identical twins, match. They have the same trait. Whereas for dizygotic twins for the same trait, only 15% of twins match for the trait. The other 85% of the twin pairs actually don't match for the trait. So if that's the case, 75% concordance for monozygotics and 15% concordance for di, when we do the differential, we see that there is still 60% of the concordance of that trait due to the genetics. That's really, really big. And in fact, I guarantee you that in any quiz or exam that you have in the future, we will always see a greater than 50% differential for traits that we claim are genetically based. It'll always be a number greater than 50 when you do this properly. What threw you all for a loop, and I was happy to see it actually, because I love when we get things wrong in the videos, because that's the time to get it wrong, right? It doesn't count against you. You get full credit just for watching it. So making mistakes in those video questions is priceless because they don't cost you any real points. There, the example said there is 100% concordance for the trait in monozygotic twins. So, I mean, that screams genetics, right? Monozygotic twins are 100% genetically identical. There's 100% concordance in those twins. It's got to be genetic. And then that question went on to say that there's also 100% concordance in the dizygotic twins. So now that's a head scratcher. Twins match 100% of the time, even when they're fraternal twins. Well, the only thing we can do to get at the genetics is to take the differential, and when we do that, we see that there's actually a 0% genetic concordance there. In fact, none of that trait is due to the genetics. That trait is purely environmental. It's due to the fact that monozygotic twins and dizygotic twins have the same exact developmental environment, and so that trait is environmental only. And that's what we were getting at there. So that's our quick refresher of concordance. What concordance is, it's the percent of twins that match. How we use concordance, let's emphasize that the monozygotic concordance in and of itself means nothing. It tells us nothing. The dizygotic concordance tells us a little bit about the environment, but solitarily, it really doesn't tell us much either. The only information that's truly worth anything is the differential when we take the dizygotic concordance away from the monozygotics. That differential is what's informative. And again, we will have a genetic component. What did I say? If our number is greater than 50%, we will say it is genetic. If that differential in our hands is less than 15%, we will say that the trait is controlled by the environment. And of course, the question that I'm sure many of you are wondering is, well, what does it mean if the concordance differential is between 15 and 50? Well, that means it's not clear whether or not the trait is genetic or environmental in the real world. But because of that ambiguity, I will never give you a concordance question that falls in that gray zone. If you do the questions right, you'll either get concordance differentials that are above 50% and you'll say they're genetically based, or less than 15% and you'll say they're environmental. I'll never give you anything in between to worry about. So there weren't any real questions about pedigrees, which was great to see. Most of you seem to understand pedigrees quite a bit, and I know you've seen pedigrees before, but I did want to take the opportunity just to give you some examples of different pedigrees and show you what to look for, because one of the things that you'll likely be asked to do in this class is either draw a pedigree and decipher it, determine what it tells you, or be given a pedigree and decipher it. So you won't be told that it's X-linked or recessive. You'll have to determine that from the pedigree. So I wanted to take a moment to just talk about what characteristics we look at. The first thing we want to look at in any pedigree is we want to determine, is it dominant or is it recessive? Which of the two is it? And we also want to keep in mind, of course, that in pedigrees, circles are female, squares are male, and filled in means we have the trait, and blank means we don't have the trait. So the first question we want to address is dominance or recessivity, and to address that, the first thing we're going to look at are what I call clades. Clades are immediate families. Oh, we got Jet's attention, it looks like. Clades are immediate families, so parents and their direct offspring, that all match in their shading, or all match for the trait. So here's a clade because the mother and the father have the trait, and so do all of their children. That's a clade. This is not a clade because even though the mother and the father match, they have a child that doesn't match them. And this, of course, is not a clade because even the parents don't match. So a clade is when they all match. And a clade always shows you what's recessive. So in other words, if the clade is all filled in, then filled in is recessive. The trait is recessive. If the clade is all not filled in, well, that means not filled in is recessive. And so what's the trait? That's right, it's dominant. Remember, the trait is always filled in. So if not filled in is recessive, then filled in, having the trait, is dominant. But here, our clade is filled in. So that means the trait itself is recessive. That's the first thing we want to answer. We know it's recessive. It isn't dominant because of the clade. Then what we want to determine is it X-linked recessive or is it autosomal recessive? So if we think back, for X-linked recessive, any mother is going to give it to all of her sons. That's the classic definition of X-linked recessive. And if we look at this, well, here's a mother that has it. She has 2 sons, and they all got it. So that really does look X-linked to us. We know this is the clade. That doesn't tell us much there. If we come here, we see a son that got it from parents here, also indicating X-linked recessive. So we want to look at mothers that have the trait for recessive traits and see if all of their sons have it or not. And that will tell us X-linked. This mother has it. She's carrying 2 recessive X chromosomes, and she's passed that on to her sons. That must express the trait because they don't get an X chromosome from their father. So then we move on to our second example. And as we look at this, unfortunately, we have no opportunities for clades. So what do we do when we don't have a clade? When we don't have a clade, the way that we determine dominance or recessivity, and remember, that's always our first job, we're always going to worry about that before we worry about X-linked or autosomal, is we ask ourselves, does it skip a generation? Does the trait skip a generation along a lineage? And here it doesn't. So the mother has it, some of her children have it, some of her grandchildren have it. We see the trait emerging in every single generation. That suggests dominance. It's not always true. On true real-world clades, it's not on real-world pedigrees, it's not always the case, but it suggests dominance. So we're going into this thinking dominant. Then what we want to wonder is it X-linked or autosomal? And we'll play with the X linkage, just as we did before, and we'll realize that if it's dominant, a father will always give it to his daughters, because to create a daughter, the father gives his only X chromosome, and if the father shows the dominant trait on that X-linked trait, then he's giving his daughters that dominant allele. And as we come here, we see here's a father, and he gave it exclusively to his daughters and not to his sons, and that's X-linked. So for X-linked recessive, mothers give the trait to their sons, and for X-linked dominant, fathers give the trait to their daughters. Moving on further, first thing I'm going to look for is some clades, and I see one. Do you see it? There's one clade here. There's the clade. The parents match, and so do their children. Here the parents don't match, here the parents don't match, here the parents match, but they have one child that's different, and that clade is always going to be recessive. Whatever the filled-in state of the clade is recessive. Here, filled in is the clade, so filled in is recessive. This is a recessive trait. Next question. Is it autosomal recessive or X-linked recessive? If it's X-linked recessive, mothers will always give this trait to their sons if it's X-linked recessive. So here's a mother that has the trait, and here's a son that doesn't. That's not X-linked. And that's the only case where we have that, but that's all we need is one case. So it's got to be autosomal. If it's recessive, and mothers with the trait don't give it to all their sons, it can't be X-linked, it's got to be autosomal. And our final condition or classification, I'm looking for clades, And I've got one. Here's a clade. And finally, we see the example of what I've been saying. The clade is always recessive. Always. So this is recessive. But what's recessive? Being not filled in is recessive. So what's the trait? The trait here must be dominant. Remember, the trait is always indicated by the filled in shape. If being recessive is not filled in, then being shaded is dominant. And then the question becomes, is it X-linked dominant or is it autosomal dominant? Well, if it's X-linked dominant, fathers will always pass it to all of their daughters. Here's a father, he passed it to his only daughter. Could be X-linked. Here's a father, there's a daughter without the trait. Can't be X-linked. Impossible for this to be X-linked. It's got to be autosomal. So a quick tutorial there on navigating your way through pedigrees, just to try to make pedigree analysis a little bit easier for you. And as long as the lab hasn't changed since I've designed the lab course for genetics, you'll be bringing in some family information of your own, if you haven't already, and be constructing your own pedigrees in lab and then analyzing them. So this will set you up for that analysis as well, which is great. All right, so let's wrap up with some overview of gene linkage, going on to the second lecture from this week. Everything we've been talking about so far has been unlinked genes. So if we had an individual who is heterozygotic for gene A and heterozygotic for gene B, we always were assuming that those two genes, the alleles for those genes, were on two separate non-homologous chromosomes. And these chromosomes assorted independently, which is why we would make two separate Punnett squares for this kind of cross and use the product rule of probability for this cross. So that was unlinked genes. When we move on to the same kind of individual who is heterozygotic for those two genes, see jet stretching there. Now in this unit we see that those genes are linked on a single chromosome. So I want to be clear here. As I drew it before, we had an individual who is heterozygotic for gene A, right? We've got a dominant allele for gene A and a recessive allele for gene A, dominant allele for gene B, and a recessive allele for gene B. That individual is heterozygotic for both of those genes. This individual is heterozygotic for both of those genes. On this chromosome, we have a dominant allele for A, and a recessive allele for A is on the other chromosome, and a dominant allele for B, and a recessive allele for B on the other chromosome. These are homologous chromosomes. So both of these individuals are heterozygotic for these two genes. In this case, we'll give this yet another term. Because the two dominant alleles are on one chromosome, the dominant A is with the dominant B, and the two recessive alleles are on the other chromosome, the recessive A is with the recessive B, we also say that these alleles are coupled in this case. And we would no longer use this kind of notation to diagram linked genes. We want to capture the linkage pattern. So we would say that yes, we've got a dominant allele for A and a recessive allele for A, but we want to show that the dominant allele for A is linked to the dominant B allele. So we would use this notation instead of this. The last case we'll consider here is an individual that has the dominant A allele linked to the recessive B allele and the dominant B allele linked to the recessive A allele. I want to point out that this individual is yet our third example of someone who's heterozygotic for both genes. We have a dominant and recessive allele for both genes. This individual is heterozygotic AB, but the linkage pattern is different. So we would write their notation in this way to show that the dominant A allele is on the same chromosome as recessive B, and the recessive A allele is on the same chromosome as dominant B. Furthermore, we would use the terminology repulsion to describe these alleles. These alleles are in repulsion because the dominant allele of one linked gene is on the opposite chromosome as the dominant allele on the other. So we have heterozygote, heterozygote, heterozygote. We have unlinked, linked and coupled, linked and in repulsion. Distinct differences there that we want to keep in mind. So that's the terminology. Now, something else changes as well. We didn't really, I try to make a big deal of independent assortment and segregation in the first unit. We certainly did as we transitioned from mitosis and meiosis to Mendelian genetics. But it's here where that idea of independent assortment really, really hits home. Again, here's one homologous chromosome, and an individual is heterozygotic for A. And here's the other pair of homologous chromosomes, completely unlinked, heterozygotic for B. And because these are unlinked and because of independent assortment and segregation in meiosis 1, we can get equal numbers of gametes that have all possibilities of these alleles. We can get the dominant A allele with the dominant B allele. We can get the recessive A allele with the recessive B allele. We can get dominant A with recessive B and recessive A with dominant B, and we get a quarter of each of these kinds of gametes in this case. And again, that's why we handle dihybrid crosses the way that we do. What we see here is that after meiosis 1 and meiosis 2, it looks as though we can only make two kinds of gametes. A gamete with the two dominant alleles together, that's when this chromosome goes to a gamete, and a gamete with both recessive alleles together, that's where this chromosome goes to a gamete. So very, very different from unlinkage. We don't even see this type of gamete and this type of gamete because these genes are linked. They travel together. They're a package deal. Except, oh boy, here's where it gets just a little bit more complex. Except we know of something that happens in prophase 1. In prophase 1, we can get crossing over. And when crossing over occurs, we make these hybrid chromosomes. Remember, pieces of homologous chromosomes trade places. And what's over here is going to switch over here, and what's over here is going to switch over here. We're going to get a swapping of genetic information from the point of recombination down. So our recombinant chromosomes are going to look like this. And our recombinant gametes are going to look like this. So then the question becomes, well, Manella, you told me that when there's no linkage, we get all four kinds. And now you're telling me that even with linkage, we get all four kinds. So what's the difference? The difference is that, relatively speaking, recombination is rare. And the lack of recombination is common. So what happened in unlinked genes is that we not only got all four types of gametes, we got equal numbers of them. 25% of the gametes we made were of each kind. A quarter of each of these were made. And while we do make all four gametes in linked genes as well, we do not, and I emphasize, we do not make them in equal numbers. So the percentages of the non-recombinant gametes are far, far higher than the percentages of the recombinant gametes. And in fact, the closer these two genes are in physical distance on the chromosome, the lower and lower these numbers get, and the higher and higher these percentages get. So let's take that through an example. Let's imagine that we do have linkage, and let's start off with these alleles being coupled. And then you automatically know that we have the two dominants on one chromosome and the two recessives on another. And let's say that recombination occurs 10% of the time. So 10% of the time, we get recombination. Crossing over happens in prophase 1 of meiosis. 10% of the time. Well, let's start with a kind of a simple thought experiment. If 10% of the time recombination happens, what percentage of the time does recombination not happen? Well, 90% of the time recombination doesn't happen. Okay, so that means that 90% of the time these stay the way they look right now, but 10% of the time, instead of them staying the way they look, we get, just as we described before, a recombination event between them, giving us recombinant chromosomes. So 10% of the time, we get this. If 90% of the time we get this, and then we go through meiosis 2, and we're going to pull these, meiosis 1 and meiosis 2, and we're going to pull these apart, what percentage of time do you think we're going to make gametes that have dominant A with dominant B? And I'll give you a hint. 90% of the time, we get all of this. So what percentage of the time are we going to get half of it? And that's right. 40% of our gametes are going to have dominant A with dominant B. And what percentage of our gametes are going to have recessive A with recessive B? The other half. So 90% of the time we keep our chromosomes unchanged, which means 45% of the time we get gametes with big A and big B, and 45% of the time we get gametes with little a and little b. 45 and 45. By the same thinking, if 10% of the time we get this, what percentage of the time are we going to make gametes that have dominant A with recessive B? That's 5% of the time, or half of the total 10%, and 5% of the time we're going to get gametes with recessive A and dominant B. If we go through the same thought experiment up here, and we think about this in terms of percentages with unlinked genes, this represents genes that are unlinked, well, that's going to be 25% of each kind of gamete. And there's the striking difference between linked genes and unlinked genes. If A and B are unlinked and we have a heterozygote for both genes, 25% of their gametes are going to be of all four types, equal amounts of each. Once the genes are linked, now we get far more non-recombinant gametes without crossing over than we do get recombinant gametes when crossing over did occur. And the number of those gametes that we get is directly proportional to the percent of recombination and non-recombination. Okay. The last thing that we want to say here is that when we do this type of genetic experiment, we always do these crosses as test crosses. Always. Always, always. In sophomore level genetics. So why do we do it? Why is the mate always a test cross mate? Well, let's think about it. If we're doing a test cross, even with the genes linked, we've got nothing but recessive alleles to give. And even if crossing over happens, it really doesn't change much, right? If this recessive allele comes over here and this recessive allele goes over there, it doesn't really change what we're doing. And then when mating occurs and we have gamete fusion, well, there's the recessive alleles there, and there's the recessive alleles there, and there's the recessive alleles there, and the recessive alleles there. There are zygotes. And if we stop and think about it, this gamete called for dominance in A and dominance for B, and even after sexual reproduction, because we only got recessive alleles from the other parent, we're still dominant for A and dominant for B. In other words, what this gamete wanted is what we see in the offspring. This gamete called for recessive A and recessive B, and when it fused with the test cross gamete, it's still recessive A and recessive B in the phenotype. What this gamete wanted is what we see. This gamete called for dominance in A and recessivity in B, and after the fertilization of the test cross, that's still what we see in the phenotypes of the offspring, and same as here. So by doing test crosses, we actually see in the offspring what each of these gametes was actually calling for. That's why we do the test cross. The last point I want to make here before we go through a real problem, a test problem of this kind, is when we say 10% recombination, we actually can convert that to a physical distance in a unit that we call centimorgans. And the unit in centimorgans is always equal to the percent recombination. So if there's 10% recombination between these genes, then there's 10 centimorgans between them, or 10 map units. We use those terms interchangeably. All right, so let's do a quick and simple kind of off-the-cuff problem, word problem, using these principles. Let's say, well, let's make it a tough one. Why not? Let's really practice a lot of different concepts here. Let's say that a parent who is heterozygotic for two traits, height and hair color, is test-crossed. That parent is tall and has brown hair. And the test-cross parent is short with blonde hair. So we start off with a single parent who's heterozygotic for hair, color, and height, meaning they should show the dominant trait for both, right? Because they're heterozygotic for both genes. They're test-crossed. We know by now from Unit 1 what that means. Mated with somebody who's recessive for everything. And the initial parent has brown hair and is tall, so now we know the traits. And the test-crossed parent is short and with blonde hair, so now we know the recessive traits as well. When they mate, and let me think for a moment. I'm using a different software to record here, so I don't think I can pause. You're just going to have to bear with me as I think for a moment and have the smoke coming out of my ears, so to speak. Let's say that 80 of their offspring are tall with blonde hair, and 80 of their offspring are short with brown hair, and 20 of their offspring are short with blonde hair, and 20 of their offspring are tall with brown hair. That's their offspring. That's the F1. And we can be asked, what is the linkage pattern of these genes in the heterozygotic parent? And we can be asked for the percent recombination. Or we can be asked for the distance in centimorgans or the distance in map units. Remember, it's all the same. All right, so let's recap and say, like, what just happened? We're told that we have one parent who's heterozygotic for the genes for height and hair color. And that parent is tall with brown hair. So it looks like tall is dominant and brown hair is dominant. That parent is test-crossed with a short and blonde parent. So it looks like short and blonde is recessive. And they have 200 offspring. Good for them. And of those offspring, 80 are both tall and blonde-haired, 80 are both short and brown-haired, 20 are short and blonde-haired, and 20 are tall and brown-haired. And we're being asked to determine the linkage pattern in this original heterozygotic parent. In other words, are the genes coupled or in repulsion? And we're being asked to compute the percent recombination between these two genes, or the map distance in map units or in centimorgans. So first thing I would do here, just as I've done in previous units, is key this. I want to get away from the words. I want to think in genetic notation. In other words, I'm going to start saying that for the height gene, we have dominance here, and for the hair, for the height gene, we have dominance here, and for the hair color gene, I guess I'll just use A. For the hair color gene, we have recessivity, right? We've got the tall trait here and the recessive trait here. So I've keyed that. And for the next 80, it's actually recessive for height and dominant for hair color. So I'm going to key that. And for this 20, it's recessive for both, and for this 20, it's dominant for both. So now I've turned all of this into our shorthand of phenotypes and genetic notation. That's step one. Step two is identifying the non-recombinants and the recombinants. Well, remember, recombination is always rare. So the recombinant offspring, or the recombinant gametes, are always going to be the smaller number. So these are your recombinant offspring, making these your non-recombinant offspring. From there we can get the linkage pattern, because if this represents the lack of recombination, then the pattern or linkage of phenotypes we see here mirrors the pattern or linkage of the alleles. In other words, one chromosome has the tall allele linked to the blonde allele, and the other chromosome has the short allele linked to the brown-haired allele. This set of traits in the non-recombinants came when this chromosome was given into a gamete, and this set of traits in the absence of recombination occurred when this chromosome was given to a gamete. So right away we see that the linkage pattern is repulsion. These alleles are in repulsion. Because by looking at the non-recombinant offspring, we see the non-recombinant linkage pattern. A dominant with a recessive or recessive with a dominant. In order to determine the percent recombination, we need to remember a very, very simple formula for this, which is the percent recombination, or the distance in map units, or the distance in centimorgans, the number is always the same, equals the number of recombinant offspring divided by the total number of offspring. Not divided by the total non-recombinants, the total. And so we go back to what we said here. The number of recombinant offspring, well, 20 plus 20 is 40. And the total number of offspring here is 200. And so if we do that math, we get 20%. 20% recombination, 20 centimorgans between these genes, 20 map units between these genes. So that's just one sample problem kind of off the top of my head of how we would use linkage and how it would differ from what we've been doing so far. Of course, we're going to have additional practice in our challenge questions this week as well. And you've got the back of the chapter questions available in Canvas under Files. Just click on Files in our Canvas classroom, and from there click on Practice Problems, and you'll see a whole slew of practice problems from the end of the textbook chapter that you can use to practice these same kind of questions as well. So that's pretty much everything I wanted to cover in this video. We've got the meaning of concordance, which was important to set the stage for how we use monozygotic and dizygotic concordance to give us genetic and environmental inputs for a trait. We talked about different pedigree examples, which is going to prove incredibly important for this unit. And then we spent the balance of our time on linked genes, first defining what we mean by coupled and repulsion, comparing and contrasting that to the unlinked genes we've talked about already. We saw the implications for linkage in terms of generating non-recombinant and recombinant gametes, and those gametes come in different numbers when genes are linked because of the rarity of recombination. We talked briefly about how test crosses are always used for these types of problems in this course, so that what we get in the gametes is what we see in the progeny. And then we went through a quick example of a kind of problem we could expect to see when genes are linked, just so we're a little bit familiar with the way we want to be thinking in this unit. So hopefully this was helpful, a little bit of a long one, but there was a lot to cover. Thank you for your patience, and of course, please let me know if anything continues to be confusing in the comment bubble that's about to pop up right now.